Hi, we are Group 11. We have chosen Kaggle project Machine Learning from Titanic Disaster as our data mining project. As everyone knows, the sinking of RMS Titanic is one of the most infamous shipwrecks in history. One of the reasons that shipwreck led to such loss of life was there were not enough lifeboats for passengers and crew. Although there was some element of luck involved in surviving the sinking, some groups of people were more likely to survive than others, such as women, children, and upper class. As a challenge, we have done some analysis on what sorts of people were likely to survive. In particular, we are going to apply few machine learning techniques to predict which passengers survived the tragedy. Let's get started by looking at the training data set. As you can see, most of the variables like name, sex, age are self-explanatory. Survived is the target variable which we are predicting, where 0 represents dead and 1 represents survive.
As we have seen in the Titanic movie, the disaster was famous for saving women and children. So let's look at the sex and age variable to see if any patterns are evident. We do a two-way comparison and display the probability of number of males and females who have survived. As you can see here, the majority of female have survived and majority of male have died. As a part of our first analysis, we had updated the target values in test set with 1 for all the females and 0 for all the males and made a submission to Kaggle. And you can see that we have ended up at 2750th position in 3300 groups. So we were able to move 570 position with the help of just one variable. Let's move on to next variable age. We can see that there are 177 missing values for age. We have imputed with average age of rest of the passengers. As discussed earlier, women and children are given importance during shipwreckages. So, we created a new variable child using age attribute where we consider a passenger as a child if the age is less than 18. We created a table with gender and child attribute to see the survival proportion. Well, it still appears that if a passenger is female, most survive, and if they were male, they don't, regardless of whether they have a child or not. So we haven't got anything to change our prediction on here. Let's look at couple of other interesting variables like the class that they were riding in and the ticket fare to see if we can find anything interesting. The class variable is limited to 3 values, but fare is continuous variable that need to be reduced to something that can be easily tabulated. Let's bin the fare into less than 10, between 10 and 20, 20 to 30 and more than 30 and store it in a new variable called fare2. While we can see that still majority of male regardless of class or fare still do not do so well. Surprisingly, we can see that female with class 3 and fare greater than $20 have less chances of survival when compared to other females. We didn't expect that such expensive tickets would be worse off in accident, but perhaps those more expensive cabins were located close to icebergs or exit stairs maybe. Whatever the cause was, let's make a new prediction based on our new insight. By marking all women from class 3 and fare greater than 20 as dead, that is 0 in the test dataset. We were just curious to know if our analysis was correct. Surprisingly, we ended up moving up 628 position from previous position in the leadership board.
Till now, we sliced and diced the data to find subsets of passengers that were more or less likely to survive the disaster. To find even more fine-grained subsets, let's look at the interaction of many different variables using simple algorithm decision tree that can do this work for us. We used gender, age, class and fare variables for prediction till now, but we never did investigate about sibling spouse info, number of parents or children, or port of embarkation. The remaining variables, passenger name, ticket number, cabin number, are all unique identifiers for now. They don't give any new subsets that would be interesting for decision tree. So let's build a tree leaving the above ones. We are using rpart library in R to build the decision tree. Let's examine the tree built. As you can see, decisions have been made using sibling spouse information variable as well as the port of embarkation one that we didn't even looked at before. On the male side, the kids younger than 6 years old have a better chance of survival, even if there were not too many aboard. It all looks very promising. We did another submission to Kaggle to check our accuracy. Nice, we just jumped 334 spots with only an extra 0.5% increase in accuracy.
Feature engineering is very important in predictive analytics, that even a simple model with great features can outperform a complicated algorithm with poor ones. Feature selection is the process of selecting a subset of relevant features for use in model construction. We'll try to chop and combine different attributes to see if it is helpful to us to make more accurate predictions. These are the new variables that we have created. Let's start with the name field. If we take a glance at the first passenger name, parts of those names strings like Mr. could be extracted to build a new predictive model. If we scroll through the dataset, we see many more titles including something like Miss, Mr., Master, and so on. There seems to be a fair possibility of patterns that may be helpful. In order to extract these titles to make new variables, we will need to perform the same action on both the training and testing set so that the features are available for our decision tree. In R, we are using the rbind function to merge the training and testing set. Now we have the new data frame called combi. We have isolated the title of all the passenger using the code this. As we can see, we have 8 passengers with title doctor and so on. Next, we have two variables that indicate the number of family members the passenger is traveling with. If we assume that a large family might have trouble tracking down kids as they all scramble to get off the sinking ship, we will combine these two variables into a new one called family size. Suppose, what if specific families had more troubles than the other? We extracted the surname of passengers and grouped them to find families, but a common last name such as Johnson might have a few extra non-related people aboard. In order to solve this issue, combining the surname with family size should remedy this concern. For example, no two family Johnson should have the same family size variable. Let's look at how family ID variable looks. As you can see, Sage is name of a family that has 11 members. All these new features were engineered purely based on our intuition. Now we will apply decision tree using the new variables created. Interestingly, our new variables created using feature engineering are used for making decision in the decision tree. As usual, we submitted to Kaggle. We just moved up 641 position by just squeezing in few variables.
Let's try to climb the leadership board by using other machine learning algorithms. Why not we try random forest? Random forest is an ensembling learning method for classification, which operates by constructing a multitude of decision trees at training time and outputting the mean prediction of individual trees. Let me explain random forest with the help of an example. Consider a female passenger from Southampton marked as S who rode in the first class. Tree 1 and 2 would vote that she survived, but the tree 3 votes that she dies. If we take a vote, it's 2:1 in favor of a survival, so we would classify this passenger as a survivor. One important thing to note is random forest cannot handle missing values. So first we need to fix the missing age values. Initially we computed the missing values for age using mean values, but we'll now try to impute with some more intelligent way. We have 263 missing values, which is almost 20% of the whole data. We'll use decision tree to predict the missing values of age using these variables and method ANOVA since age is a continuous variable. We replaced the missing values using predictive values using the following R code. Now we are ready to run our model. The syntax is very similar to the decision trees but with few addition options. First one is importance argument, which allows us to inspect variable importance, and the next one is the entry argument, which specifies how many trees we want to grow. Let's look at the importance of variables. The mean decrease accuracy tests to see how worse the model performs without every variable. So a high decrease in accuracy would be expected for most important variables. The other one, Gini 1, essentially measures how pure the nodes are at the end of the tree. Again, it tests to see if each variable is taken out, a high score means the variable is important. Unsurprisingly, our title variable is at the top for both measures. We were pretty happy to see that the remaining engineered variables are also doing quite good. After making the submission, we got to know that our model doesn't seem to well on test data. As you can see, what we can interpret from this is smaller the datasets, sometimes a fancier model won't beat a simple one. But we did not give up here. We kept trying other ensemble models available in the market. After applying various models, we found C-Forest performed the best for this dataset. Before proceeding further, let's see what C-Forest is. C-Forest generates an ensemble of trees of same form as C-tree, with random features selected at each node. C-tree uses permutation-based significant test procedure in order to select variables instead of selecting the variables that maximizes an information measure, thereby avoiding the potential bias which is present in normal decision trees. After submitting the C4S result to Kaggle, we ended up at 286th position among 3,454 teams, which is within top 8%. Thank you.